What came back from Voyager 1 did not look like a cry for help. It looked worse. It was a signal that shouldn't have existed at all, out beyond every planet, beyond the pressure of the solar wind, beyond the region where the sun still feels like the ruler of a system. The oldest active spacecraft humanity has ever built was still answering Earth. It was receiving commands. It was staying pointed at home. It was alive. And yet when NASA listened, the spacecraft seemed to be speaking in a language no one recognized. Not silence, not static, not death, something stranger. A machine launched in 1977, built with the logic of another century, floating more than 15 billion miles away, had started sending back data that looked wrong in a way engineers hate most. Not random enough to dismiss, not clear enough to understand. It was as if Voyager 1 had become trapped behind its own voice, still talking, still breathing, but unable to say what was happening inside. That raised a terrifying possibility. If NASA could no longer trust what Voyager was telling them, how would they know whether the spacecraft was healthy, failing, or only moments from disappearing forever? How do you diagnose a patient when the heartbeat reaches you 2 days late, and every question you ask takes nearly a full day to arrive? But hidden inside that broken transmission was a clue. Then another. Then a pattern so old, so fragile, and so improbably recoverable that it forced engineers to do something that sounds almost impossible: rewrite part of a spacecraft's mind across interstellar space. Because the real mystery was never just what Voyager sent back. It was why a machine that had survived Jupiter, Saturn, the edge of the heliosphere, and nearly half a century of radiation and freezing darkness would suddenly begin speaking nonsense now. And the answer to that question leads to something even bigger. It reveals what deep space does to machines, what time does to human engineering, and why one faint signal from the darkness can still change the way we think about exploration, survival, and the terrifying loneliness between the stars. Voyager 1 matters because it is no longer just a spacecraft. It is a presence. A human artifact moving through a place no human being has ever seen, carrying instruments, memory, and a message from Earth into an ocean of interstellar night. It is farther away than anything we have ever built, which means every whisper it sends home is more than data. It is proof that something made by human hands still survives where almost nothing should. That is why this mystery hits so hard. When a mission is new, failure feels technical. Disappointing, expensive, fixable. But Voyager is different. Voyager belongs to history, to imagination, to that part of us that still wants to believe our reach can outlast our lifetimes. If a machine this old can keep working out there, then perhaps the line between our small world and the enormous dark beyond it is not as final as it feels. And yet that faith depends on one fragile thread: communication. Voyager 1 does not fly back for repairs. No crew can intercept it. No emergency rescue exists. There is only radio. A signal crossing billions of miles at the speed of light, arriving weak and ancient, carrying the condition of a spacecraft that left Earth when disco was new, and many of today's engineers had not even been born. If that thread frays, the mission doesn't just become difficult, it becomes unknowable. That is what made the strange signal so unsettling. NASA was not just losing data, it was risking the ability to understand whether humanity's most distant explorer was still functioning in any meaningful sense at all. Somewhere, in that impossible distance, a spacecraft was trying to tell us something. The problem was that no one knew whether the message described a minor glitch, a dying system, or the beginning of the end. And because Voyager 1 is the only human-made object directly sampling that region of interstellar space, any failure would mean more than the loss of a beloved mission. It would mean closing a window no other spacecraft can reopen anytime soon. To understand why that garbled signal mattered so much, you have to go back to the beginning, to a time when Voyager 1 was not a legend, but a gamble. The spacecraft launched on September 5, 1977, into an era when computers were primitive, memory was tiny, and much of what we now call the outer solar system was still more myth than landscape. Voyager 1 and its twin, Voyager 2, were built for a rare planetary alignment that allowed one-mission architecture to slingshot across the giant planets using gravity like stepping stones. The original dream was audacious enough on its own: fly past Jupiter and Saturn, transform dots of light into worlds, and send back images and measurements no civilization had ever possessed, it did exactly that. Voyager 1 reached Jupiter and exposed a place of violence and complexity beyond expectation. It helped reveal Jupiter's faint ring system. It found new moons. It delivered close views of worlds that no longer looked like distant ornaments, but like active, dynamic places with histories of their own. Then came Saturn, where Voyager found new moons again, new ring structures again, and one especially powerful reason the mission's trajectory changed forever. Titan. Titan mattered because its thick atmosphere hid its surface and hinted at chemistry with profound implications. To get the best look, Voyager 1 took a path that bent it upward out of the plane of the planets. That decision gave humanity one of the great close encounters in space exploration history. But it also meant Voyager 1 would never continue on to Uranus and Neptune the way Voyager 2 did. Instead, it became something stranger. A departing witness, climbing away from the known architecture of the solar system and heading toward the frontier no probe had crossed. Then, in 1990, came the image that would permanently alter how Voyager lived in human memory. From about 40 astronomical units away, Voyager 1 turned its camera back toward home and captured the famous family portrait of the solar system, including Earth as a tiny speck suspended in a shaft of sunlight. That pale dot was so small it almost disappeared, and because of that, it made everything feel larger. Voyager had shown us not just where the planets were, but what we were. After that, the planetary tour was over, the cameras shut down, the glamorous part of the mission ended, and what remained was, in a way, even more extraordinary. Voyager kept going. Its official interstellar mission began in 1990, aimed at the outer limits of the sun's influence. This was no longer about dramatic flybys or spectacular photos. It was about invisible structures, charged particles, magnetic fields, plasma waves, the shape of the heliosphere, the nature of the boundary between our stellar neighborhood and the wider galaxy. It was slower science, deeper science, the kind that transforms understanding not with a single famous image, but with years of lonely measurements. In December 2004, Voyager 1 crossed the termination shock, entering the heliosheath, where the solar wind slows dramatically as it pushes against interstellar space. Then, in August 2012, it crossed the heliopause and became the first human-made object to enter interstellar space. Not another planet, not another moon, another environment entirely. That moment was historic, but it also marked the beginning of a new kind of vulnerability. Voyager was now in a region no spacecraft had ever operated in before. Radiation, cold, aging systems, shrinking power reserves, and the sheer delay in communication turned every engineering decision into a slow-motion wager. Each year, the spacecraft lost a little more electrical power as its radioisotope thermoelectric generators weakened. Each year, NASA had to decide what to shut down, what to preserve, and how to squeeze meaning from a machine that had already surpassed every original expectation. By then, Voyager 1 was no longer simply following a mission plan. It was being kept alive through ingenuity. That is part of what made the first hints of trouble so unnerving. Because long before the biggest communication crisis, Voyager had already begun reminding engineers that age changes everything. In 2022, NASA reported a strange issue involving the spacecraft's attitude articulation and control system, the hardware responsible for keeping Voyager properly oriented. The system appeared to be working because the high-gain antenna remained pointed at Earth and the signal strength had not collapsed. Yet the telemetry it sent back didn't reflect any plausible onboard state. In other words, the spacecraft seemed to be behaving correctly while describing itself incorrectly. It was the kind of contradiction that makes deep space engineering feel almost psychological. Was the sensor lying? Was another system corrupting the data? Was the problem serious or only strange? NASA kept monitoring. Voyager kept flying. Then, in November 2023, the real mystery arrived. This time, the problem was bigger. Voyager 1 was still receiving commands from Earth, and mission controllers could tell the probe was still operating. But the science and engineering data coming back had become unreadable. The spacecraft was speaking, but what it said could no longer be trusted. For the people responsible for a probe more than 15 billion miles away, this was the nightmare scenario between life and death. A silent spacecraft is tragic. A talking spacecraft that makes no sense is worse because it leaves you trapped in uncertainty. Somewhere in Voyager's ancient systems, something had failed. But where? The signal delay turned every test into an act of patience so extreme it barely feels human. A command took roughly 22.5 hours to reach the spacecraft and another 22.5 hours for the response to return. Nearly 2 full days for a single exchange. Imagine trying to repair a failing machine in another city. Now replace the city with interstellar space and stretch every conversation across almost 45 hours. The first task was narrowing the possibilities. Voyager had several key onboard computer systems, each responsible for different functions. The fact that the craft still responded to commands meant not everything had collapsed. The fact that it remained pointed at Earth meant its orientation systems were still, at some level, doing their job. That was the first thread of hope. The spacecraft was not lost. Its body still obeyed. The problem seemed to be in how its internal information was being assembled and transmitted. Eventually, NASA traced the issue to the flight data subsystem, a critical part of the spacecraft that packages science and engineering information for transmission. Somewhere inside that ancient logic, data was no longer being handled correctly. Engineers were effectively trying to diagnose a half-century-old computer operating in an environment nothing on Earth can perfectly simulate, with documentation from another era at a distance so absurd that mistakes could take days to reveal themselves. And then came the astonishing part. Rather than abandon the damaged area and accept partial blindness, the team found a way to work around it. They devised a plan to take the affected code and divide it into sections, storing those sections in different places in the flight data subsystem's memory. That meant rethinking how pieces of the software talk to one another, updating references, and rebuilding logic pathways inside a spacecraft launched when memory itself was measured on a radically different scale than today. This was not the dramatic kind of repair people imagine from science fiction. No sparks, no robot arms, no heroic astronaut in a suit. It was more fragile than that. A patient relocation of instructions across a failing mind, one command at a time, to a machine older than most modern laptops' operating concepts, floating alone in interstellar space. On April 18, 2024, the team sent the first major modification. Then they waited. About 22.5 hours later, Voyager received it. Another 22.5 hours after that, the answer came home. The fix had worked. For the first time in 5 months, NASA could read usable engineering data from Voyager 1 again. They could finally begin checking the health and status of the spacecraft with confidence. That was the moment the mysterious signal started to make sense. Not because the spacecraft had been hiding a dramatic external secret, but because humanity had managed to decode the failure of one of its oldest and most distant machines. And yet that breakthrough did not close the story. It opened a bigger question. If engineers could restore engineering telemetry, could they restore science as well? Could Voyager become more than merely reachable again? Could it return to being useful? That second discovery is what turned a successful rescue into something almost miraculous. Restoring engineering data was like hearing a patient's pulse. Restoring science data was like hearing them speak again. After the April breakthrough, NASA kept pushing. The mission team executed a second step in May 2024 to begin bringing science data back. 2 of Voyager 1's 4 operating science instruments returned to normal first. The others needed more work. For a while, the probe existed in a liminal state familiar to anyone who has watched an old machine come back to life. Improved, responsive, but not fully itself. Then by June 2024, NASA announced that all 4 science instruments were once again returning usable data. Voyager 1 had resumed normal science operations for the first time since the problem began in November 2023. That mattered enormously, because Voyager 1 is not just a symbol drifting in the dark. It is a functioning scientific outpost in interstellar space. Its surviving instruments study plasma waves, magnetic fields, and particles. Those measurements tell scientists how the heliosphere behaves from the outside, how pressure fronts move through deep space, and how the sun's protective magnetic bubble interacts with the material between stars. Before Voyager crossed into interstellar space, humanity had theories about what the outer boundary of the heliosphere might look like. But theories are shaped by distance. Voyager transformed them with direct evidence. It showed that the edge of the sun's influence was not a simple, clean boundary in the ordinary sense. It was dynamic, structured, and full of surprises. Even after crossing into interstellar space, the spacecraft kept finding signs that the region was more complicated than a textbook diagram suggests. That is why the restoration of science data was bigger than an engineering triumph. It preserved a unique scientific conversation with a place no other spacecraft is sampling directly. Lose Voyager, and that conversation goes silent. But there was something else hidden inside the recovery, something even more unsettling. The farther Voyager travels, the less margin for error exists. By 2024 and beyond, NASA was no longer merely maintaining a spacecraft. It was negotiating with aging hardware at the edge of possibility. The mission had already turned off heaters and non-essential systems to conserve power. Components were operating in colder conditions than engineers once expected them to survive. Thrusters were aging. Internal systems were becoming harder to predict. Every problem solved carried with it the knowledge that another one was coming, and another one did. In late 2024, Voyager 1 experienced a separate communications interruption when its fault protection system unexpectedly switched off the primary X-band transmitter and turned on the weaker S-band transmitter instead. At that distance, that mattered. The S-band signal was far fainter, and Voyager 1 had not used it to communicate with Earth since 1981. NASA eventually re-established communication and restored regular operations, but the incident reinforced a hard truth. Even after the famous garbled signal mystery was solved, Voyager remained perilously close to the limits of its own endurance. Then there was the thruster problem. By 2024, engineers were also dealing with clogged thruster fuel tubes caused by silicon dioxide buildup over decades. These tiny thrusters are critical because Voyager must keep its antenna aimed with incredible precision toward Earth. If the spacecraft cannot point home, it might still exist physically, but for us it becomes unreachable. In September 2024, NASA completed a risky thruster swap by briefly turning off a main heater to free enough power to warm an alternate thruster branch before bringing it into service. That alone sounds difficult. In truth, it was exquisite surgery performed at a distance where every motion is separated from its result by nearly 2 days. And even that was not the last chapter. In 2025, NASA revived another set of Voyager 1 thrusters that had been considered unusable for decades, in part because the Deep Space Network's Canberra dish, the only antenna with enough power to send commands to the Voyagers, was scheduled for a lengthy upgrade period. The team wanted backups ready before command capability became more constrained. Think about that for a moment. Engineers in the mid-2020s were still resurrecting forgotten hardware on a spacecraft from 1977 because they needed every possible option before a single critical antenna on Earth went offline for maintenance. This is what makes Voyager such a powerful story. The science is extraordinary, but the persistence is almost unbearable. Why does all of this matter beyond the romance of deep space? Because Voyager 1 is teaching us how long human technology can survive when no rescue is possible. Every solution NASA invents for Voyager becomes part of a broader lesson in designing missions that must endure isolation, radiation, uncertainty, and delay. Those lessons matter for probes headed to the outer solar system, for future interstellar precursors, and even for long-duration missions closer to home. How do you build systems that degrade gracefully? How do you preserve science when power declines year by year? How do you manage machines that must keep functioning long after their designers are gone? Voyager also matters because of what it tells us about our place in the cosmos. Earth is noisy, immediate, crowded with signals. Voyager exists in the opposite condition. It is a tiny engineered object suspended in distances so vast they humble language itself. And yet from there, it still sends back evidence, not poetry, not philosophy, measurements, reality. The universe beyond the sun is not just an idea anymore. Voyager touched it and kept talking. That changes humanity's emotional relationship with the unknown. Interstellar space used to belong mostly to imagination. Voyager turned part of it into a field site. There is another reason this mystery resonated so deeply. It exposed how exploration is never only about discovery. It is also about maintenance, compromise, and the willingness to keep solving problems long after the applause has faded. The public often remembers missions for their firsts: first flyby, first landing, first image. But some of the most meaningful work happens later, when aging hardware refuses elegance and survival itself becomes the achievement. Voyager's strange signal was, in a way, a perfect symbol of that phase. Not glamorous, not cinematic in the obvious sense. A machine whispering nonsense from the dark, and a group of engineers deciding that nonsense was worth listening to until it gave up its meaning. The human drama inside that decision is easy to miss if you only focus on the spacecraft. By the time Voyager entered its late 40s, almost everything about operating it had become difficult. The power supply drops by about 4 watts each year. Systems that once had comfortable margins now live at the edge of necessity. Heaters once considered essential had to be turned off. Instruments had to survive in colder conditions than planned. The old assumptions built into onboard fault protection no longer mapped neatly onto the stripped-down reality of the mission. So NASA's team was not working from luxury. They were working from attrition. The people handling Voyager inherited not just a spacecraft, but decades of decisions, legacy hardware, old documents, old code, and a design philosophy from an era that could never have imagined the mission still operating this long. Every anomaly required historical archaeology as much as modern engineering. What did the original builders intend? Which redundant systems still existed? Which had been dormant for decades? Which risks were survivable and which could kill the spacecraft outright? When the garbled data crisis hit, solving it meant more than technical skill. It meant patience strong enough to survive delayed feedback, humility in the face of incomplete information, and creativity sharp enough to imagine workarounds for hardware nearly 50 years old. It meant teams studying architecture built for the age of punch cards and sending corrections into a region of space no human can inspect. And because of the communication delay, even emotional relief came late. When engineers watched results arrive from Voyager, they were not watching the present. They were seeing what had happened almost a day earlier. Success, failure, danger, stability, all of it was delayed, already written by the time Earth learned about it. That distance changes the psychology of mission control. You cannot intervene in real time. You can only prepare, transmit, and wait. It is less like piloting and more like sending faith across a void. The latest confirmed developments make that balancing act even more dramatic. NASA has continued trimming Voyager's systems to preserve the mission as power declines. In February 2025, the cosmic ray subsystem on Voyager 1 was shut down to save energy. In April 2026, NASA shut down Voyager 1's low-energy charged particles instrument as well, leaving 2 science instruments still operating: the magnetometer and plasma wave subsystem. At the same time, the team has been working on a more ambitious energy-saving strategy, nicknamed the Big Bang, designed to swap groups of powered devices for lower-power alternatives and potentially extend operations even further. That means the story after the mysterious signal is not one of simple recovery. It is one of controlled sacrifice. Voyager survives by becoming smaller. Each instrument turned off is a loss, but also a trade. Less capability now in exchange for more time overall. That is the brutal arithmetic of extreme longevity in deep space. The mission is deciding, year by year, which pieces of the spacecraft's scientific life to preserve, which to surrender, and how to keep just enough of its senses awake to justify another season in the dark. And still, even diminished, Voyager remains unmatched. No other active mission sits where it sits. No other probe is directly measuring that environment from so far beyond the planets. Even 2 instruments are enough to keep the interstellar conversation alive. So what happens next? In one sense, the future is simple. Voyager 1 will keep going outward, farther from Earth with every second, carrying less power each year, surviving through a combination of stubborn hardware and increasingly delicate engineering decisions. NASA will continue turning off systems when necessary. It will continue testing ways to stretch heat, energy, and communications beyond what once seemed reasonable. Each success may buy months, sometimes a year, sometimes, if the team is fortunate, a little more. In another sense, the future is full of unresolved mystery. Voyager is approaching a milestone that sounds almost poetic, 1 light day from Earth. That means there will come a point when even light, the fastest thing in the universe, will need a full day to cross the distance between our planet and this spacecraft. By late 2026, Voyager 1 is expected to become the first human-made object ever to reach that threshold. A command sent from Earth will effectively spend a day in flight before it arrives. The reply will need another day to come home. Conversation with Voyager is becoming not just delayed but monumental. And beyond that lies the true unknown. How long can the remaining instruments last? How long can the spacecraft stay warm enough, stable enough, and communicative enough to remain useful? Will the Big Bang power strategy extend the mission in meaningful ways? Could dormant systems be revived again if needed? There are answers NASA does not yet have, because no one has ever operated a spacecraft this old, this far, in this environment. That uncertainty is not a flaw in the story. It is the story. Voyager 1 is no longer racing toward a destination we can map in dramatic milestones. It is drifting into a future shaped by probability, ingenuity, and attrition. Every month it survives adds a little more knowledge and a little more wonder. Every anomaly reminds us that the mission lives in a state somewhere between persistence and miracle. And that brings us back to the signal. At first, it seemed as though Voyager had turned into a riddle, a machine sending messages that looked meaningless from the edge of interstellar space. The temptation, in moments like that, is to imagine something cinematic in the wrong way. A secret transmission, a cosmic interference, a dramatic external force. But the truth was more powerful because it was real. The mysterious signal was the sound of age. It was what happens when human technology survives so long and travels so far that failure itself becomes cryptic. It was a spacecraft continuing to obey, continuing to point home, continuing to try, even as part of its internal voice broke down. And the reason that story matters is not because Voyager hid some fantasy in the darkness. It matters because we answered it. Across billions of miles, with antique hardware, thinning power, and delays that would break almost any normal operation, human beings listened closely enough to recover meaning from apparent nonsense. They found a way to restore communication not by conquering distance, but by enduring it. That is one of the purest forms of exploration there is. Voyager 1 left Earth carrying a golden record, a set of sounds and images meant for whoever might one day encounter the spacecraft. But perhaps its greater message was never the record itself. Perhaps it is the fact that almost half a century later, we are still in conversation with it at all. Not because the universe made that easy, because people refused to let the conversation end. So somewhere tonight, beyond the planets, beyond the heliosphere, beyond the familiar architecture of home, Voyager 1 is still moving. The spacecraft is colder now, quieter in some ways, simpler than it once was. Some of its senses are gone, others are still awake. And when it turns its remaining instruments toward the interstellar dark, it is doing something no other machine can do. It is telling us what lies outside the sun's last breath. And back on Earth, after all these years, we are still listening. If that story stayed with you, stay with the mission. Subscribe for more documentaries that treat space not as background spectacle, but as one of humanity's greatest ongoing stories. If Voyager 1 still amazes you, leave a comment with the moment that hit hardest, because the reactions to these stories are part of why they keep getting told. And if there's someone who still believes exploration matters, send this their way. The farther Voyager goes, the more extraordinary it becomes that any signal at all still finds its way home. For factual grounding on the recent and historical details used here, I relied on NASA and JPL mission updates covering Voyager 1's unreadable telemetry issue. The April-June 2024 restoration of engineering and science data, the later communications and thruster incidents, the 2025-2026 power-saving shutdowns, and Voyager's mission history and